Hi, in this video we want to take a look at building regression models. So this is an example that has some features that are interesting. So this shows more of the way that we actually think about regression as we actually build a model. So once again, we're working through an introduction to statistics with Python. And here is the GitHub URL for where I got the code for this and the data. All right, so what we want to do, we want to build a linear model in Python. All right, so first thing we're going to do, we're going to go ahead and get matplotlib pyplot. Then we're going to get pandas, numpy. All right, now we're going to pull in ordinary least squares from stats models. And then we're going to get interaction plot, AB line plot, and QQ plot. All right, so the interaction plot tells us, do we need an interaction term in our model? We use that to inform us. AB line plot is for just plotting lines. And then the QQ plot is for judging the distribution of a variable. And we're going to need a linear model ANOVA along the way. So let's go ahead and pull that in. Now let's go ahead and get some matplotlib stuff going. All right, on this example, we have some IT salary data. And you know, there's some variables. So we've got experience, and we've got education, and we've got management level. And what we want to do is we want to build a model that predicts salary using experience, management, and then education in these. So experience is an integer value because it's experience in years. Management is a categorical variable. It's binary, 0 for non-management, 1 for management. And education is ordinal, 1 for bachelor's, 2 for master's degree, and 3 for PhD. Or in regression, when we have ordinal data, we treat that the same as categorical data. Mathematically, in the way that we handle it, it works out to be the same. It's tempting, it's very, very tempting to run like something like ordinal data, like education, 1, 2, 3, as a numeric vector. Don't do that. Almost never do that. The times that we do that is when we're in big data and we can't get things to converge. But that's very rare. In general, don't do it. Treat it as same as you do with categorical data, which means that I'm going to need dummy variables. Now, when I have categorical data that's represented in zeros and ones, I'm good on the dummy variable aspect. I don't really have to worry about that too much. I can leave it as is. But education, I actually need to make sure that it's interpreted as categorical data. All right, so here is the base URL, or the URL period. So let's go ahead and pull in that data. I'm going to call it salary.table. So let's go ahead and just look at the first few lines. All right, so experience is X. And we can see the first few rows have 1, 2, or 3 years of experience. Education, 1 means bachelor's degree, 2 means master's, 3 means PhD, and then management, 1 means they're management, 0 means they're not. Okay, so let's go ahead and just take a look, and I'm just going to go ahead and define these E, M, X, and S vectors, so that way I have them to pull out whenever I need to. All right, so now let's go ahead and let's plot this to see what we can get. So what we're going to do, first thing I'm going to do, I'm going to plot a figure. So I'm just going to get the figure overall going. Now I'm going to add a subplot to it. And I'm going to go ahead and put some labels on there. So X label is experience, Y label is salary. Now, beforehand, looking at the data, we know that the X lim is going to be 0 to 27. And then the Y lim is just under 10,000 to just under 30,000. And we'll go ahead and put some symbols in there. All right, our management labels are non-management and management. Our education labels are bachelor's, master's, PhD. Our colors are going to be red, green, and blue. And our factor levels are E and M. Now, something that's kind of cool about this, when I go and do this whole thing, if I look at this for loop and how this is all set up, and I dig into the details of it, what we've got, we can see that the shape course, so the diamond corresponds to non-management for all 3. The color corresponds to the education level. So red means they're bachelor's, green means they're a master's degree, and blue means that they're PhD. Okay, so just look at the colors right now. We can see what the difference is between these. So here I have the non-management bachelors, or red diamonds. Here I have the the management bachelors, doing better. Now, if I look at the green non-management, that's for masters. If I look at the green management, that's masters also. And then for PhDs, that's going to be in the blue. So the PhDs are coming in just a little here, just a little bit above the master's counterparts. And then here with triangles, management PhDs. So something that's kind of interesting off of this, we see that, you know, given the level of experience, the management with masters are actually getting more than the management with PhDs. Now, this is going off of the average of it overall. So, you know, something that could be affecting this is that there probably are fewer PhDs running around in this organization. All right, so now let's go ahead and let's fit a linear model. So my formula is going to be that salary depends on education, management, and years of experience. Why do I have the C in here? Because they're categorical data. So since I want education to be categorical, I want management to be categorical. Just let you know, since I've got zeros and ones, this special case, zeros and ones for the management, I don't actually need to put a C around it. Mathematically, it will work out. But I need the C around the E's because you know, a 1 for bachelor's, a 2 for see, bachelor's is 1, master's is 2, and PhD is 3. That is ordinal data. We don't, you know, it's not like there's like an equal gap between these levels. All right, so let's go ahead. Now here's my linear model. So notice I'm using the formula in here and my data. So here I have formula, then the data, and then I want to pull out the fit. Let's take a look. All right, so we can, you know, we can look through and see that's, you know, ordinarily squares, you know, degrees of freedom of residuals, and the covariance type is non-robust. Our R squared is 0.957. That is pretty high. F statistic is 226.8. That is pretty good. So our p-value for the F statistic is darn small, and our log likelihood is negative 381.63. We want that to be maximized as much as possible. And AIC, BIC, so these guys here, these three, we really need to be looking at multiple models to be able to even use these. So they really don't tell us one model by itself. Now here we can use the p-value on each of these to determine should the coefficient actually be 0. So here's the coefficient, here's the standard error, here's the t value for the t-test, and here's the p-value corresponding to this. So here the hypothesis test is that the coefficient is actually equal to 0. And we include that none of these are equal to 0, which means we want to keep them in the model. If a coefficient is 0, that means it has no impact on the model from a statistics point of view. Therefore, we would throw it out, but I don't need to throw anything out here. And we have some other things to look at. Nice. So remember, when I talk about the residuals from a regression model, residuals always add up to 0. If they add up to 0, that means the mean is also equal to 0. So something that we'll take a look at is the skewness. That's pretty close to 0. Our kurtosis is, so depending on how kurtosis is defined, that's either going to be equal to 0 or 3, I think it's 3. So that's not too far off. Okay, so let's go ahead and let's keep looking at this. All right, so now something we always want to remember, if I see my R squared and my adjusted R squared, if those are different from each other, like substantially different, if these two values, R squared and adjusted R squared, if I see those separate, that means that I have an indication that I have vectors in there that are not contributing to the model, and I need to throw out some predictors. And we use F statistic to, judge the model, and that looks pretty good. Now, log likelihood and AIC, these are really only useful if I have multiple models to compare. It isn't, there's information in there, but it's kind of like, when I use those, I want to see which among competitors are give me the best results. And so when I look at the residuals, we ideally want the skew to be 0 and the kurtosis to be the same as the normal distribution, because we want to have the normal distribution for our residuals. All right, and so here we can look at the modeling matrix, which we can look at as a data frame. So here's our modeling matrix. So what this does inside, so when I did the regression model previously, underneath the hood, Python put a vector of all ones in there. Then it converted the education categories into dummy variables. So dummy variables have either zeros or ones. So in this column, if they have a master's degree, so value of 2 for education, if they have a master's degree, they have a 1. If they have a bachelor's or a PhD, it's a 0. In this column, if they have a PhD, then it's a 1. If they have a bachelor's or a master's, it's a 0. So here I can see that this employee has a bachelor's degree because they have neither a master's nor a PhD. If I look down here, I can see that this employee has a PhD. And I can see that this employee has a master's degree. All right. And down here, remember 1 for management tells me that they are in management. 0 means they're not. And then here is years of experience. And that's a numeric vector. Okay. So let's go ahead and take a look at another way to see this. And here's the original data, just so that we can take a look back at it when we go through and look at the code some more. All right, so now what we want to be able to do, let's say an employee, someone is thinking about moving to the company, and they ask, hey, how much will I probably get? Well, we want to make a prediction. So here we take the features of that person and we predict what they're going to get for payroll. So for this particular person, they have 12 years experience. They have, they're going to be coming into management, and they have a PhD. How much can we expect them to make? All right, and there's the number. So that way we could be able to tell them, hey, this is how much you would make if you jump ship over to our company, more than likely. Now what we want to do, we want to check the residuals. After we build a regression model, we want to check to see the residuals. We want, first of all, we want them to be normally distributed. So the most important aspect of that is that it's not skewed. And then after that, we have to have the dispersion around 0 for the residuals has to look like a bell curve. And it doesn't have to strictly look like a bell curve, but the main thing is we don't want skewness in our residuals. That's the very first thing we want. We want constant variance across all the possible values. So let's take a look at the residuals, and let's go ahead and plot it. All right, now I'm looking at this, and I can see a pattern in my residuals. So when I look at each of the different education and management levels, I can see kind of like grouping of the residuals. Because I can see that, that means that we have a bad model. There's a problem with our model. I should not be able, so if I knew what the residual is, I can say what is a likely value of the, for the predictor, or for the predictor vectors. So if I tell you the residual is around 1,000, you know that it's probably either education 1, management 0, or education 2, management 1. One of these two. Anytime that we see a pattern in our residuals, when I plot them in relative to the y or the target variable or the predictor variables. If I see a pattern, I know I have a problem in my model. And then we start digging in, but that's more for a regression class. Here we're only touching on regression. We just know that there's, at this point in this class, we just know that there's a problem. All right, so what we want to do, we want to improve our model. So let's go ahead and let's introduce an interaction term. So I believe from looking at the original plot, so if I look back here, I can see that we kind of like have these lines going all the way across. So it's like each level, each combination of education and management looks like it has a different y-intercept, but they all have the same slope in terms of experience. Okay, well, yes. So let's go ahead and let's just try a model. Now, this is not going to be our final model, but let's go ahead and look at a interaction term between experience and education. And then let's go ahead and start fitting the model. Ordinary least squares. Let's see what we get. And, you know, I'm going to clear the console and to take a look. All right, what we got? What we got? All right, my R squared is 0.96. My adjusted R squared is 0.955. I still think that's okay. That's close enough. Once it gets to be more than 0.01, 0.02, something like that, I start getting worried, but this is close enough for me. And in general, you can expect the adjusted R squared to be less than the R squared. All right, so I look through here, and it looks like the p-value is saying the intercept is statistically significant. All three levels of it, so the dummy variables, the dummy variables for education are statistically significant. The management level is statistically significant. Years of experience, statistically significant because the p-values are so low. But now when I get down here, if I'm using the 0.05 criteria, I can see that the interaction between education and years of experience, those are not statistically significant for both of the interaction terms. Okay, all right. Well, let's keep on working on this. So let's go ahead and let's take a look at ANOVA, where I look at the previous linear model and the interaction term linear model. So in this, what I want to do is, are these models for all practical purposes statistically giving me the same amount of information on that salary? So when I do ANOVA on two different models, I'm asking, are these models giving me basically the same information on my target variable? And so if I fail to reject the null hypothesis, they are equally informative. If I reject the null hypothesis, they are different. Okay, one of these models is more complicated than the other. All the coefficients, all the predictor variables in one model are in the other one, but the other one has something added. All right, so the interaction term is the same as the previous linear model with the interaction term added. Okay, why is that important? Because if I conclude that these are equally informative and one is simpler than the other, I want the simpler one. All right, because I want to keep it simple, stupid. All right, so what I want to do, I'm going to check the p-value. I'm going to go, hey, are these equally informative? Yes or no? Well, let's take a look. All right, so I see here, I've got a p-value of 0.16, or that's bigger than 0.15, so I failed to reject the null hypothesis. I conclude that these two models are equally informative. Okay, if they're equally informative and one is simpler than the other, I want the simpler one. Okay, why do we do that? First of all, simpler models are easier to interpret. They're easier to work with. Also, I'm less likely to overfit. Okay, so because of that, I want the simpler model. Which one's simpler? It's the one without the interaction term so far. Okay, so I conclude that the model without the interaction term is actually the better model to go with. And here's another way to print it, print that p-value. Another way that we can print that out. All right, here's a way to print out coefficients and constants. All right, so now let's change it up. Now what I'm going to do, I'm going to build a model that has salary depending on years of experience plus an interaction term between the two categorical variables. Okay, what is this going to do? This is going to create a slope line. So I'm going to get a slope off of this one because that is a numeric variable. I'm going to have a slope. And then for each combination of education and management, I'm going to get a different y-intercept off of this. Well, if I look back up here, that's exactly what I said previously at the beginning of the video, that here it looks like I have a constant slope for each of these lines. The difference is that they're parallel to each other, so therefore they have different y-intercepts. All right, so let's go ahead and build that model. Now let's take a look at this one. Now my adjusted R squared is nearly perfect. Wow, 0.999. Adjusted R squared is 0.999. That is stellar. That is outstanding. That is amazing. This is probably the one to go with, but let's not count our chickens until they're hatched. All right, so here I've got my p-values going down, and all of them are equal to 0. All right, I'm feeling pretty good about this. Here I can see what the coefficient is for each of these. I want to go through and do some computations with it later down the road. All right, so now let's compare the original linear model to the interaction model that we have now. All right, let's go ahead and redo this just so that we can see it. All right, so I'm doing ANOVA on 2 models, and one of them has predictor variables, and the other one has the same predictor variables plus something else. Okay, so if we remember, the linear model is the experience, management, and education. The interaction is going to be experience, education, management, plus interaction between the two. We've got interaction between education and management. All right, if these are statistically equal to each other, that interaction term means it's not useful. If they are statistically different from each other, then that means that the interaction term is giving me a lot of bang for my buck, and I want to keep it in there. All right, so let's take a look. All right, my p-value on the ANOVA is, wow, that is small. I've got my p-value, the exponent is -31. All right, that means I have to go negative 0.000000000000000 30 times, and then I get a 3. All right, that is a lot of zeros. So this is super, super, super small. That means I conclude, I conclude that we reject the null hypothesis in favor of the alternative. The alternative hypothesis is that the 2 models are different from an information point of view. All right, if they're different and both of them have like the same predictors, except one has one more on there, then I know that the one more on there is adding something to the model. And so I want to keep that. That one more on there is the interaction term. Okay, so let's go ahead and keep working on this. So now I'm feeling good. I'm digging this model. I hope you are excited as I am about this. So now what we want to do, we want to look at the residuals of our model. All right, so after we start feeling good about our model, we start looking at the residuals to see that, hey, can I even trust the ANOVA test? All right, to be able to do ANOVA, my residuals have to be normally distributed. I have to have constant variance with respect to all predictors. We have to have, and they have to be independent and identically distributed. And we have to have mean zero. Mean zero is automatically going to be in there because of how we construct regression. So we don't really think about that. So but the big ones are independent, identically distributed, constant variance with respect to the predictor variables. Yeah, I'll just stop there. That's good. All right, so let's go ahead and pull these out. All right, so now let's go ahead and plot this. Let's see what's going to happen. Okay, what I want to see, so down here is the x value. This is the predictor variable. I want to see that everything is centered on 0. The average is 0. I want to see that they're constantly, like the dispersion away from above and below 0 is roughly symmetric, and they're kind of like evenly distributed. And in terms of being above or below 0, they appear to be normally distributed. Okay. Oh, also something I need to say is that here we're using studentized residuals. Studentized residuals are something specific to regression. If I'm doing a machine learning problem, I'm going to use regular residuals. That's just model minus observed, model value minus observed, and that is just my residual. If I'm using studentized residuals, there's an adjustment for the variance of the difference between the deviation and the statistical construction of deviation. So it's not a 100% pure system. The studentized versions perform better in general, but we only have that when I do regression, like classical regression. I don't have it when I do machine learning. If I have the option, I want to use studentized residuals instead of regular, but it's only for special cases. All right, now I look at this, I want to have the residuals above and below 0 be distributed by a normal distribution and kind of evenly distributed throughout. Well, what do we see around x value of 10? Look at that. That is a huge deviation from 0. If I'm normally distributed, everything, almost everything is from -3 to 3. This bad boy is giving me a -6. Okay, there is a problem. This observation is giving me an outlier. When I have an outlier, I have 3 choices. The first choice, ignore the thing and proceed it like it's not there. You should still know about it and be aware of it, but you proceed forward. Second option is kick it out. That means omit it from the model. Third option is to replace the values of that observation with values you believe are correct. We do that when we realize that there's like an entry error or there's a mistake, there's fraud, something like that in our data. In general, the classical way to do it is either ignore it or kick it out. So for this one, the classical way to handle this would be to kick it out. All right, when would I not want to do that? If I have very little data, then it's, so if I can identify why it's an outlier because like somebody wasn't paying attention, someone used meters when they should have used feet, there was a sensor error, I know otherwise what the value should have been, then I want to replace it. That way I don't lose the data point. Another thing we might do is we might impute if I don't want to lose that value of data. That's another option, and where I would use another statistical technique to replace those values when I can't figure out on my own what the value should be. Omitting is usually the best way to go unless I'm in like a small data situation where each data point is super, super valuable. All right, so what we want to do, we want to double check. Is that truly an outlier? Maybe it's right, maybe it's wrong. I don't know. I'm going to double check it. So we're going to go ahead and we're going to do a hypothesis test. We're going to do an outlier test on this bad boy. Whoops. So let's take a look. All right, so this for each of the rows of data, this is giving me a p-value for a hypothesis test. And I can see that, All right, I've got 0.98, 0.96, or this is 0.99, 0.96. Go up. All right, 0.96. I mean, everything below the first row on this, and here is the index for where it's located. Everything after the first row is statistically not significant. But when I look at the very first one, that p-value is super, super small. All right, that's exponent of -16. That is small. Okay, so my hypothesis test is that the null hypothesis is that the observation is not an outlier. The alternative is the observation is an outlier. Okay, and something we can do to double check is I only have one outlier and I only have one value with a p-value less than 0.05. Okay, so I conclude that this observation for 32, whatever value that is an outlier. So now I need to make a decision. What do I do? Either I can ignore it, I can get rid of it, I can drop it, or I can replace the values, and overwrite. All right, I don't know about the data. I don't know how it was recorded. I don't know anybody to talk to about this. So I'm going to kick it out. I'm going to get rid of it. You're out of here. So what I'm going to do, I'm going to get rid of observation 32, and I'm going to use the drop. I'm going to use drop to do that. I'm going to drop it like it's hot. Okay, so here's the index of what's left. And you'll notice that 32 is gone. So now I'm going to rerun the model, just missing with that one data point. I have to basically go through and double check everything that I did before. So here, this is going to be the linear model where I have experience, education, and management, but no interaction. No interaction. I'm waving my arms and no. All right, so let's take a look. All right, so I've got R squared at 0.96, adjusted R squared at 0.95. P-values are all small, good. So I'm feeling good about this regular linear model by itself. Now let's go ahead and build the interaction model. So here, I've got education interacting with years of experience and then plus management. And when I look at this, I can see that I'm not really feeling it for the interaction between education and management, but the rest I'm feeling good about. So let's go ahead and run ANOVA on this. All right, so once again, the p-value for the ANOVA test between this type of interaction and so education and experience is greater than 0.05. All right, so from my hypothesis test, I failed to reject the null hypothesis. I conclude that the two models are equally informative. Because they are equally informative, I want to take the simpler one. Simpler one is the one without any interaction terms. Okay. Now let's keep on going. Let's do another interaction model like I did before, but this time I'm looking at the interaction between education and management. This was the better model before we removed the outlier. Okay, so I look here, my p-value is super, super small, -46 exponent. That's super, super small. Okay, what this tells me is that the two models are statistically different from each other. So the null hypothesis is that the two models are equally informative. The alternative hypothesis is that they're not equally informative. One does a better job than the other. Okay, so what we need to do, we need to figure out which one's the better one. Well, it's in this case, it's the one with the interaction term, because the two models all have the same predictors, except one has an interaction term added on. Okay, so we conclude that the interaction model for this one is better than the regular model. And that's consistent with what we got before. All right, so here are the residuals. And what we want to do, we want to take the standardized residuals and we want to plot them. All right, so what I want to see the residuals centered on 0, vertically wise. I want to see a constant dispersion above and below 0, and I want to see the dispersion like not change as I go from left to right in terms of the x value. So what would be a bad result on this? If I saw like a cone, or I saw a shape, or I saw like, if I see any pattern in there, let's say I saw like a circle or something weird like that, that would be bad. I want to look like this random scattering of plots where I cannot detect a pattern in the residuals as I go from left to right. I don't see a pattern in this. All right, so I'm feeling good. All right, so now let's go ahead and plot some stuff. Take a look. And that looks pretty good. That's pretty cool. So here, this is, I'm just, going through and plotting the model. And that's pretty close. Right now, what we want to do, we want to build an interaction plot. Usually, we do this before we add an interaction term to guide us on, do we want to have interaction? Okay, so I've got education and I've got management. And I've got these set up, and so the y-coordinate is the mean of the salary among all the people with that particular value. The red corresponds to management. The blue, or so non-management, and the blue corresponds to management, and then bachelor's degree, master's, and then PhD. And what we want to see, so we conclude that we should have an interaction term if the lines are not parallel to each other. So if the lines look like 90 degrees from each other, if they're like this, so they don't have to cross, but you see that the lines look 90 degrees, that is strong interaction, or strong indication for interaction. If they look like railroad tracks, then that leads me to believe I should not have an interaction term. Here, I'm seeing a slope on this and a slope here. So that there's enough of a difference that I conclude that we should have an interaction term, which we've already confirmed anyway. Okay, that's all I've got. I know that there's a lot in this, but this is good stuff. This is exciting stuff. This process of build a model, check a model, compare a model, build a model, check a model, check your residuals, get rid of outliers. That's more of a back and forth aspect of actual model building. When I build a model at work, so just to let you know, I am professionally not a professor. I do not teach as a primary job. This is just a side gig for me. I do data analytics all day. This back and forth aspect is the real method of how we build models. If I want to be able to make an inference on something using regression, or I want to make a prediction using regression, I build a model, build another model, and I start comparing, and eventually I go, hey, this is what is the best of the models. And then I go to my boss, I report, and my boss is happy with me. I have a good job, I have a good life, and I leave early even though I'm supposed to be on the clock. All right, so I hope you're staying happy and healthy. Please let me know if you have any questions.